Okay, guys, we're going to continue on today learning about uniform motion problems. So in our table of contents, our TOC, uniform motion 43 and 44. Might even go a little bit on 45, we shall see. So make sure you write that on your TOC, uniform motion. Let's go ahead and Roberta. Okay, so when we talk about uniform motion, what is that in reference to? This is a type of motion where the motion of an object in which the object travels in a straight line and its velocity remains constant along the line as it covers equal distances in equal intervals of time. Regardless of how much time. So, for example, imagine you're out running and you run 3 miles. Well, maybe the rate at which you're running during the first mile is not the same as which you're running at the end of your run, right? Well, with uniform motion, that doesn't take into account. It doesn't say, oh, well, they're probably faster in the beginning and slower at the end. The expectation when we're looking at uniform motion is that that person would have been running the same distance during the same amount of time constantly. So however long it took them to run the first mile, it would take them exactly that amount to run the second mile, exactly that amount to run the third mile. That is what uniform motion takes into play. Is it maybe realistic in a real world? No. So when you find the rate, you're actually, in reality, finding almost like someone's average rate or average speed at doing something. So how are we going to go about doing this? Well, first off, we need to know that sometimes we're going to be looking at this in terms of one vehicle or one object, and other times we're going to be looking at this in terms of 2 objects. So we're first going to look at uniform motion of one object. So number 1, calculate the rate of each part of the trip using the formula D equals RT, distance equals rate times time, solved for R. So we learned with literal equations we could solve for R. And if we solve this for R would equal distance divided by time, or d divided by t. And we need to make sure there is unit continuity. So when we're talking about uniform motion of one object, we're talking about when they have told us this object, this person, this car, whatever it is, has moved this distance in this amount of time. And it's also moved this distance in this amount of time. Find the average rate of those two things together. So that's how part of it is. That's why when we talk about part one and part two of the trip, imagine if it took you 15 minutes to walk to your friend's house, and then when you left that house and you came home, it took you 25 minutes to walk. And they want to know what is the average speed of all of your walking together. So that's what this is going to help us do. Second, substitute the information from step one and the problem into the formula. So we should remember that R stands for rate, T stands for time, and D stands for distance. So this, when we write this formula, we're not going to have to write everything out. So S, which S is going to represent the speed or the average speed of the trip, is going to equal the rate of part one times the time from part one plus the rate from part two times the time from part two, all over time from part one plus time from part two. And if there were more than two parts, if there were 5 parts, we would have to do this. We would have 5 different sections up here, and then we'd have 5 pieces below added together. So here we're going to put S represents speed or average rate. So then once we've filled out this formula, we then have to, solve the equation or complete the math to get the final answer. So if they were asking us to find average speed, we would have all of these parts and we would put them in and just do the math, and we're going to come up with S. But maybe we know S and we know some of these pieces, but there's one piece that we don't know. We would have to solve for that. So that would be more like an equation. And the last piece is write your solution sentence with context. So remember, when you're writing, you want to, if it's about a train or a car or Jimmy, you want that information in the solution sentence, and you want to say what they're doing. So let's look at an example problem. It took Ariel and Tim 40 minutes to skateboard 5 miles. The return trip took them 30 minutes. What is their average speed in miles per hour for the trip. Okay. Um, so we know the trip there is 5 miles. And since it says return trip, we also know the return trip is 5 miles. We have the two different times. But remember that in order to fill this out, we first have to calculate the rate. And that rate is distance divided by time. Now, continuity of units. They give us information using minutes, but we have to state our answer in hours. Okay? So the first thing I'm going to do is I'm going to convert these minutes to hours. Now, how would I use that? How would I do that? Well, I would use dimensional analysis. So for step 1, I'm going to do 2 different steps. I'm first going to convert to minutes to hours. So I know 40 minutes, and I would want to get rid of minutes here. So 60 minutes is in 1 hour. So 6. And secondly, I would have 30 minutes over 1, and I would have 1 hour over 60 minutes here. So this one's pretty easy. 30 over 60 is going to give me 0.5 or 0.50. Here I'd wind up with 40 over 60. If I cut that down using tens, I would be 4 over 6, or 20s would be 2 over 3. And if I divided that 2/3 is worth that 0.666667. So I'm just going to round this to 0.67. So 40 minutes is actually 0.67 of an hour. Half an hour is half of an hour. I'm converting that because that's what my final answer asked me to do. If I wanted to, I could find their rates per minute and then convert it to miles per hour. But I just converted it to start off. So now find the rate. So the rate of part 1, according to what I'm supposed to do up here, is the distance divided by the time. So my distance was 5 miles, and my time is 0.67 of an hour. And over here it's 5 miles, and it's divided by 5. So how many halves make up 5? Well, there would be 10 halves to make 5 wholes. Over here, 5 divided by 0.67, that's going to be approximately, I'm using the little approximate there because it's going to be a never-ending decimal, and I'm going to round it to the hundredths place, 7.46. So now I'm ready to do step 2 and put everything into the formula. So their speed is going to be equal to the rate of part 1. My rate is 7.46. Times the time of part 1, which was 0.67, because remember I converted everything to hours, plus the rate of the second part, which is 0.50, and the time was, 10, 10, and 0.50. Another way to look at this is essentially they were traveling 10 miles per hour in the second part of the trip. And in the first part of the trip, they were traveling about 7.5 miles per hour. So then time is 0.67 plus 0.5. So I'm going to wind up with 4 point, and this is again going to be a very big decimal. So I'm going to go out a couple places on it. Here I doubled it and went out to the 10,000ths place. And this is going to approximately equal 8.545. So if you're not told to round to a specific area, plan to round to the hundredths place for your final answer. And if they want, if you're going to have to round to the hundredths place, typically you want to keep more than hundreds around until you get to that last step. Otherwise, you kind of lose something in translation. So this was step 2, and over here was step 3, doing the math. So step 4, write the solution sentence. The average speed that Ariel and Tim traveled over the 2 parts of their trip was, I would accept 8.6 or 8.55, 8.5, and it just makes sense to actually round it to the tenths here, 8.66 miles per hour. Because no one says, they traveled 8.55 miles per hour. But 8.5 miles per hour, 8.6 miles per hour, someone would say that. So that's just one object traveling over different sections at different speeds, and we're trying to find that average speed. The second one is looking at uniform motion problems of 2 objects. Let's go ahead and 44. So steps, uniform motion, two objects. And this is going to be really similar to the steps we took when we were doing like a weighted average or a weighted mixture. So number 1, determine and name the unknown object with a variable. Number 2, organize the questions, information into a table. And we're still going to have like 4 rows here. So we're going to have object 1, object 2, and of course if we have more than 2 objects, we're going to need more of those. And lastly, we're going to have not like so much a total, but a distance. So here we're going to put the rate that each object was traveling, how long they were traveling for, and as it showed us up above, distance equals rate times time. So I'm going to multiply the rate and time together to get the distance. And the distance I'm going to put down here. Typically on the total line, this is not going to be something you fill out for these 2 boxes, just the final total. So step 3, write an equation, and you're going to use the form distance equals rate times time using the 3rd column. So like when we did mixtures, these 2 are going to represent one side of the equation, and the distance is going to be the other side of the equation. Step 4, solve the equation. And step 5, write your solution sentence. And as always, that solution sentence needs context. So I'm sure some of your parents might remember these types of problems. If you tell them about them, they'll be like, oh God, I didn't like those problems. But I'm showing you a super simple way to solve them. So two trains are 550 miles apart, heading towards each other on parallel tracks, because, parallel, we don't want them to crash into each other. Train A is traveling east at 35 miles per hour. Train B is traveling west at 45 miles per hour. When will the trains pass each other? So a couple things. If the trains were traveling at the exact same speed, that would be pretty easy. We would just take our distance, divide it in two, and divide it by how fast they're traveling, and we'd know how much time it would take to get there, right? But in this case, they're not traveling at the same speed. Track B, or train B, is traveling faster than train A. So by the time they meet, I would expect that train B has covered more distance than train A, but they are still going to pass each other, just not at the exact halfway point. When they say pass, they're not asking like they have to truly go past each other. Basically, imagine two parts of the train, and when exactly do they hit side by side, right? Side by side. So I guess not hit, they're not crashing, but like when are they first going to cross each other's planes? So let's make our table. And we know that we have train A, we have train B, and we have our distance. Right, so I'm taking right from above. Our object 1 is train A, our object 2 is train B. Okay, the rate. We know that train A is traveling at 35 miles per hour. We know train B is at 45 miles per hour. We know time spent is, we don't know. We don't know how much time N is taking or how much time B is taking, but we do know it will be the same amount of time. Okay? So A and B are actually only traveling for the same amount of time. They're just not traveling the same distance because they're not traveling at the same speed. And lastly, distance. Well, we know that for train A, however, they're going to cover 35 miles per hour. So if they cover, everybody's traveling for 2 hours, that's 70 miles for them. If it was 3 hours, it would be, 105 miles. So rate times time gives you how much distance that train covers. Rate times time tells you how much distance this one covers. And altogether, they're covering 550 miles because that's how far apart they are. So even though they're coming from two different locations, here's the start, they have to cover the whole 550 miles. But where they meet, they're not going to meet halfway through because they're not traveling at the same speed. They're probably going to meet over here. If train A was traveling faster than B, then they would be meeting over here of the midpoint. So the distance of the two trains must equal the total distance. So 35n plus 45n must equal 550. 35 plus 45 is 80n, must equal 550. I'm rewinding right now, so divide by 80, and n must equal about 6.88 hours. So I could say the two trains will pass in 6.88 hours. Now remember, this is 88 hours does not represent minutes or seconds. You would have to convert that 88 to minutes and seconds if they wanted an exact amount of time, okay? So in order to do that, we would have to be like 0.88 of 60 minutes and do all that. We're just gonna leave it at 6.88 hours. So the two trains will pass each other in 6.88 hours. And if we did find out the exact time, it would be 6 hours, 52 minutes, and 30 seconds. And that would be me taking 88%, right? 0.88 of 60 because there's 60 minutes in an hour. This is sufficient enough. And that's how you do uniform motion of two objects. Now today you have two GPs, one over each type of uniform motion that are in your digital notebook. If you have any questions, please let us know.